Today, we're going to talk about a big homework due next Tuesday. And this is combinations of everything we talked about before. And I already have the homework assignment PDF file in your in your lecture 3B PDF file, but I will post it again in detail. Okay? And let me just go to Canvas so everybody see. No, Excel is something you need to develop. And originally, I only wanted to give you the old lecture notes without the, some hint. So I decided to just give you more than the PowerPoint. I give you more hint, okay? And let me go. You know what? Let me just open up and show you what I have. Okay. If you go to lecture 3B, you guys should see a homework set. And basically, it's this table we're trying to build. And each one of them, originally, in my homework, I only show you FT. You need to figure out how to linearize it. And I'm kind of like just, might as well just give you as much as I can. But you still need to build it yourself, okay? And the files you need to plot is log st against t, log st against log t, log, negative log. This is natural log. And so look at x-axis, either t or log t, or gamma, since it's chi-square, a special case, is square root of t. So everybody agree with me? Your x-axis, either putting down t or log t, and really t in your is time or x, and in reality is your f inverse function. You guys follow me? Originally, our plot is t against ft, right? When you draw your, here, let me show you one example. Originally, when you have your t and ft, x-axis is your t, y-axis is your ft, right? And then if you use 1 minus, that will give you the survival function. And then finally, you need to plot it against log st to linearize it. So your homework basically is about how to generate a bunch of linear line. So far, so good? Your final output is a bunch of linear line, and what we call is linearizers. And why we want to linearize this? Because if you know something and something can turn into a line, what does that really mean to you? You can take advantage of your DOE using regression. Agree? So we can use linear regression if we know how to linearize it. That's the purpose of this exercise. So, all that's, dating, how long you have to wait, the machine, how bad it's going to be. Sooner or later, we still need to turn a real world situation into a regression so we can find a slope and intercept. So look at every Excel file, the PDF I give you, is we need to turn them into a line. So far, so good? So totally, how many lines are you going to play with is this slide. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them, okay? And the thing is that y-axis is a little more than just t. It's either you take the log of your survival function, and survival function is 1 minus your CDF failure function. So log st, but when you take log, remember I said even in some extreme situations we can have logs, 3 log. But usually, okay, when you take the log of log, you put a negative sign in. Why is that? Because the distribution is from 0 to 1. So once you take the log of that, it becomes negative. So if you want to do a log of a negative function, there's nothing you can do. So you need to take the negative log of the negative log. Okay. So usually, if you see log inside log, you probably will see a negative sign. And then we have normal, log normal, or gamma function. We're using the normal inverse function to get to that. And finally, for logistic or log logistics, we will use the ratio between success and failure. Okay, so basically, we need to your homework due next Tuesday. Generate 9 linear lines, and now I'm going to do it one by one, and I'll do it, but I prefer you not just copy paste. I want you to try to do it yourself as much as possible. So first, okay, I'll come up with some alpha and beta value for my Excel function. So the t is this. I'm just from -1 from 0.1 all the way down. The reason I didn't use 0 because if you use 0, you got into a lot of jump at the very beginning, making the curve looks ugly. So far, so good. T is an increment. Ft, so we'll use Ft function. Basically, is this function, right? Which one I'm doing right now? Oh, hold on. Sorry. Ignore what I just did. I jumped too quick. I should be in this Excel function. T is still a tiny time increment. Ft is what? Is this function. 1 minus negative. Okay. And what do we use for lambda? Lambda I set at 10. And if you set lambda, for example, at 8, everything changed a bit, changed to 5, changed to 11. So if you have different arrival rate, your curve will change. And let me give you a little, look ahead. So what are we trying to do later? We're trying to give you a set of data. You said that, okay, based on this set of data, if this is exponentially distributed, what will be the lambda? And right now, lambda is a parameter that you can monkey around with, but later is based on your data. And then if we want to say, oh, can I improve my lambda, make it smaller or make it big in order to have better distribution? Now you start saying that, okay, should I buy more time? Should I buy more equipment? Should I delay my maintenance time? You will do something to make the lambda a little bigger or a little smaller, okay? But right now, we're just monkey around with the number. We're writing science fiction right now. Lambda is whatever you want to do, okay? So first, Ft, St is what? Yep. I will tell you, avoid 0 right now. Using 0.001, it will be even better. But watch, okay? If I use 0, okay? Oh, it didn't jump much this time. But let me explain this to you. Usually, I want you to start from a very, very close to 0, but not 0 number, because some of the distribution at 0 tend to create a lot of jump. You probably already seen that in your previous exercise. And right now, since our job here is to visualize how this thing's gonna work, I don't want to, create a lot of hassles just with one initial value, okay?
And then how far did you want to do it? Like 2, 1?
Right, my example, I used to 1. You can go to even further. Yeah. Basically, I want you to generate the shape.
Okay.
So,
Like, as long as it generates the shape.
yeah, see here, I didn't start from 0, right? This suppose here. in this case, I can start from 0. Not too bad. Okay, so everybody agree with me? CDF is a function from 0 to 1, right? So ST will be a function from 1 to 0. Agree? And the shape, how quick this elbow point turn, depends on my parameter. So if I use a tiny parameter, it's flat. I use a huge parameter, it curve really bad. Agree? So first, you know that lambda changed, the survival rate changed. Next, how to linearize this. According to this, people look at this. Ft equal to this. Can I take log on first? Can I take 1 minus on both sides? So that become 1 minus Ft. Agree? And then if I try to get rid of that exponential, I just take log. And once I take log, it becomes lambda t. So if I divide it by lambda, t equal to these things. So, or the F inverse function equal to these things. I give you the answer already. You're supposed to develop from the first equation to the bottom equations yourself. Look at the first one. Can you do it by yourself? If I give you the top function, that's the exponential distribution, can you turn them into the bottom function?
So is ST that whole first upper function, and what's FT in your
Ft,
in your Excel? That equation is based on what's in that cell.
this is my Ft, right? Look here.
Okay.
That's my Ft. And St is my 1 minus, right?
Okay.
And then log St is log of 1 minus Ft here, right? Agree? And then this one, this one is very easy to double check. Look at this column. What should be this column? Is exactly the T column, right? Right? T to Ft. Now, I'm just turning it back, inverse. So, see, column A and column E should be exactly the same. Agree? Because I inverted. So now, if I plot log St against the T function directly, I should have a straight line. Okay? Everybody, wiggle your finger if you didn't get it. Or you look at this, you basically said, okay, I see everything now. Young man in the back, you good? You good? You're good? Okay, so first one, you should be able to do it yourself. Okay? Now, Pareto function, and we'll play the same game. Okay? Pareto distribution, I told you guys, is extreme distribution is usually used for income, right? The income, some people very, very rich, some people very, very poor, then the Gini index shows that is not a good distribution. Okay, so now first you build your T and increase, okay? You can start from 0, but sometimes when you start from 0, you deal with that blip, okay? And what's your Ft? Ft function is equal to, okay? And you need to set up a Tm, your starting time, and our start reference time is 0.09, and my alpha function, let's just play with it, okay? If I make my alpha equal to 2, see it curve really, Yeah, you can use that's what I'm trying to do right now. Look, when you're done, this is a toy you're supposed to play. So look at TM. If I set it not 0.09, I set it up at 0.5. It curved really, really bad. So 0.9, and let me change my alpha. Okay, if I change my alpha to 0.5, see how it curves? So right now, this is just, manipulate a function, big deal. But later on, the big deal is I give you a set of observation. You need to tell me what kind of alpha, what kind of TM this set of function gonna be. And as a system engineer, why you need to know this? Because then you make the life easy. Because you only control 2 parameters and said that, oh, based on this distribution, you use those 2 parameters, things will change. The argument is like when you take your quality control, why you learn normal distribution? Because normal distribution, you only need to know 2 parameters. Give me the mean, give me the standard deviation, I can change the bell shape immediately. Location and how to spread, agree? So here we're doing the same thing, just a lot fancier than normal distribution. The parameter right now, they're fake. Well, I can fake any number I want, but later on, it's something you need to investigate, okay? So here, again, ft equal to this guy. Look at the equation. I give you the manipulation. Ft equal to this. So 1 over this side, 1 minus this equal to log. And then if you take the log, alpha is down, the division becomes subtraction. So become log Tm minus log T. From this equation, you can turn to the second equation. No problem, right? Yeah, this is supposed to be part of your homework. You need to figure out yourself. I decided last week that might as well just give it to you. But people, can you look, the first equation and second equation, they are the same thing. Both sides, can I have 1 minus ft on this side and this side become Tm over T to the alpha. And then once I take log on both sides, this side become log 1 minus alpha T, Ft. The other side become alpha exponent coming down. Inside the log part, log Tm minus log T. Everybody see the second equation? No problem? I consider this is high school algebra. Okay? And then after that, you basically said, let me have the log T on one side, the rest of the stuff on the other side. So it becomes log Tm divided by alpha and this. And finally, if I want to get a T out, I just say a T equal to what? Exponential of all this yada yada. Okay? Everybody, one more time. Can you see 1, 2, 3, 4, how, all 4 equations, how the transitions happen? Good? Now we just need to play with it. So how we play with it, St equal to 1 Ft, and then this one, when I plot it, I already show you that since you have an exponential here, if I take the log on both sides, basically I plot this against log T. So Ft look like this, St look like this. This, if I look at the Excel, not Excel, I mean this guy. I already told you, for Pareto, plot the log St against log T. You should see the linear relationship. Okay, here. Plot, here's the log St, and this is a constant, this is a constant, this is a constant, so this will linearize it. Okay? So if you plot this one, you can see if I plot log St against log T, I get a perfect line. Okay? So second distribution, Pareto, I linearize it. Victoria, you see it or you have a problem? Okay. Then we'll move to this third one. Gentleman in the back, no problem, right? Okay. If you can visualize it now, it's a piece of cake of homework. But if you cannot visualize this, you could struggle whole night and just couldn't. You know your bottom line is, I need to turn this distribution into a straight line. And usually people, easy for me to give you lip service. It's just a bunch of log T, log FT. But if you don't do it right, you're not going to see that line. Weibo, same thing. First, you have a T. You have a, let me get this one up. You have a, if k equal to 1, this is your exponential distribution. So you have your ft done. And then for the ft is st is equal to 1 minus ft. And then 1 over st is this one. And then 1 over log 1 over st and plot against log t. Okay? So now you have this one log against the other one. Oh, one more. People see what I did here? Here, if you plot log 1 over st is the same thing as you plot negative log st. Agree? 1 over st, when you take the log, equal to negative log, right? Because the 1 over is the inverse component, negative 1 exponent. Okay? Any column you want to see in more detail, or every column is clear? Okay, so going back, Weibo, look at Weibo and exponential. They're almost the same, except that you have that k component on the top. So when you plot this, okay, rather than plot log st, you need to log again. Why you need to log again? Because you have the exponent the k part on top, right? You have this negative. You see, the two things different because you have this extra k there, exponent there. So you need one more log to linearize it. So if you take log rather than log, you will linearize it. Okay? And I already told you, if you out for job interview, need to in your vocabulary, Weibo is a shape distribution. Exponential is a special case of a Weibo distribution when the k shape parameter equal to 1. But if it's greater than 1, it go up. If it's less than 1, it's coming down. So you will generate okay. In exponential distribution, we consider that it's no memory, so it's a constant. But if it's increase, means what? It's increasing more than constant. So the exponent become greater than 1. But if it's drop, kind of like decaying, drop below 1. So you will have the less than 1 shape parameter. So exponential is a special case of Weibo. When the shape parameter equal to 1 in Weibo, it's exponential distribution. Okay? This, even you didn't take my class, say you only have ARENA or you only have OR1 or OR2, you should know this. Okay? I told you, when I work for airlines, when I work for insurance company, I never really see anything exponential, but exponential is always a good starting point. Okay. Next, on gumbo distribution, gumbo look like this. Okay. Let me plot it. Bring it up. Okay. FT this time is really ugly. That got an exponential of the negative exponential of the power here. So people, when you see 2 exponential, how many log you think is going to need? 2 log, right? To bring it down. So first step, 1 log, and then 1 log you become this part, and then you take the negative on this side, so the other side become exponential negative t minus mu, like a z-score things. So first equation to second equation in gumbo, you can see it, right? And then what you're going to do, take another log, become log. So this side become log. You get rid of the exponential on this side. So this equation and this equation's second equation and third equation you can generate. And finally, how to get rid of the t, bring the beta over here, bring the mu over here, so become mu plus beta times log this. This is our fourth equation. Everybody can see that, right? And since I already gave you the answer, I will say that gentleman agreement, lady and gentleman's agreement. Please do it yourself. Pencil, paper exercise from the first equation to the last equation. Make sure you can do it, because the Excel really just a mechanics based on that set. So first T, okay, and then FT, okay, and then ST, 1 minus, and then log, okay, ST, and finally, okay, when you plot the things, is T against this. Oh, by the way, you guys probably notice why I start my T early at negative 1.5 rather than start from 0. That is because gumbo function at the beginning, it got a little bit of taper asymptotic part, and I want to get rid of the asymptotic part, so I let it start early. That way, from 0 on, it looks as linear as possible. Follow me? This is just for aesthetics purpose, okay? And later on, I will give you some exercise in SAS. Those things will be done by SAS directly. You don't need to worry about it. And right now, okay, 2 things, people. Exponential, so you will have log. And then you have an alpha and your beta in order to balance it, to linearize it. Okay, this is gumbo distribution. Problem? No problem? Okay. Yeah, I think your homework shouldn't be as hard, since I give you some of the hint, more than just that 1 page. Normal distribution, you need to have the t function, and you have to have your st function, ft function, and you can use earth function to get to that f inverse done. Okay, so that is based on the earth function here. Okay, ERF function. And when you do the normal distribution, you can get it that way. Okay, and then you can have your ST done. And of course, you can find your normal inverse, okay, by doing using normal inverse function with your mu and sigma. And so look at this column and this column. If you do it right, they should be exactly the same. The other way to do it is, well, actually these two are the same way. Okay. And how you're going to plot, you just, rather than plot your inverse function and your t, you can use either column to get the job done. We're not really interested in normal distribution. We've done enough normal in your DOE and quality control. What we're really interested in is log normal. But log normal, what is the headaches? Now, everything you're talking about is not t is normally distributed. Is what is normally distributed is once you take the log of the t, and this whole thing is normally distributed. So compare normal and log normal. T and log t are the difference here. Okay? So you just repeat the same things, and this time you will have your t increment and your log distribution, and you can have your log distribution using your ERR function. And so people look at here, this two, one I'm just cheating. Say, Excel, give me a log normal. Okay? And what's the other one I did? Is, let me use the ERR function to generate that log normal. So compare the B column and C column. I'm doing exactly the same thing. I'm just cheating once. Say, hey, Excel, tell me what log normal look like. And if I use my function, can I generate the same things? And so one way you can do that is do this. Oh, no. Plot the two side by side. Oh, there's another way you can do this. Just get a correlation coefficient between B column and C column. What do you think will be the correlation coefficient between the two? They are exactly the same things. What will be the correlation coefficient? 1, right? 100%. Yeah. And the other way you can do is do this. Sum difference. Sum square and I think let me see, what's that called? Oh, sum differences x minus y square. Okay, and this is usually how I check if my student give me a report or a thesis to review, and sometimes I have okay, this number is small enough, right? Consider that's 0. Okay. Yeah, that's the way how I check. They must be highly correlated. It's 1. The difference between the two is almost nada. The sum of square is almost nada. Then I know the left and the right pretty much doing the same thing. Okay, so going back, I have my FT, then I can either use B column or C column to generate my ST. And then once I have my FT and my ST, I will start playing with the log T. Okay, and then I will have the normal inverse log function done. And what am I really looking for is to look at my inverse function, and here I can inverse back and get my exponential, exactly the same thing. But now if you plot it, log T against the one I told you. Plot log normal is plot this guy against this guy. Again, you should have a straight line. Okay? Everybody happy? Okay? I know this is labor intensive, but I promise you, you only get tortured once. Okay? I just want you to get a feeling of this. Okay? And now next, let's do gamma. Gamma is annoying. Remember, we have that t minus 1 factorial, the gamma function we need to worry about. Okay? And I'll be honest with you, I always have problem to get a gamma right. So this one, I'll just show you using gamma distribution directly. I don't need you to use the gamma function, because the gamma function at the end the gamma function is xt minus 1 factorial. The computation can be really, really annoying. Okay, and here's the gamma function 1 over gamma. I just make that constant. Done. Okay, and my ST. Okay, step by step. Here's cheating, just using the gamma function. I generate that, and then I will find the square root of t, and then I'll plot a gamma inverse. Okay, and ft inverse, I'll recover back to t. Okay, people, so far, every exercise, do me a favor at the end, have a F inverse done to show that whatever the science fiction you start, you go turn, but at the end you can turn them back to t. Okay, let me go back one more time. Look, exponential, I have t, I recover my F inverse back. Agree? It's invertible. I'll quiz. Young lady, why ordered you? Your turn. But you can ask your friends to help you. Okay, tell me, why distribution CDF function is an invertible function? So is from 0 to 1, and what's the magic word? It's increasing, I agree, from 0 to 1, increasing over a domain of t. But why that is invertible? No. That things, does it coming down and going up, curve, it's monotonically from 0 to 1. So if it's monotonically, means from x to y, it's the same thing as y coming back to x. You follow me? Yeah. So people, the reason I ask you this is every distribution you need to show that you can invert it back. See here, t inverted back. So if you can linearize it, that means you can invert it. If you cannot invert it, you cannot linearize it. Okay? So how's my timing control? I'm good, right? Okay, good. Okay. Now, we have our gamma function done. And finally, I would like to do log logistics. Log logistics, remember, there's a magic term, okay? The magic term is called odds ratio. The odds ratio is the ratio of survival versus the failure, I'm sorry, failure versus the survival. So look at the distribution look like this. Okay. Step one. You will have your F here. First thing first, both sides inverted, and then let me see if I can use logistic distribution. Logistic regression. Okay. People, look at here. If P is the probability of failure, 1 minus P will be the power, the probability of survival, right? And then I said that, so any given time, or given any given quantity, X or T, there's a ratio between failure over survival. So if I have head is survival, tail is failure, or whatever. If I have a fair coin, the upstairs is 0.5, downstairs is 0.5. 0.5 over 0.5 equal to 1, or log 1 equal to 0, means that whatever you try to explain, got nothing to explain. However, okay, if P is really, really big, this is very, very small, then this odds ratio becomes very, very big, even I take the log. Then that means that something can cause these things to fail very quickly. So it will be top heavy, or something could make this, for example, say the failure rate is very, very unlikely, 0.000001. And then the bottom will be 0.99999. So this ratio will become very, very big. I'm sorry, very, very small. Okay? So this whole things, we call it odds ratio, can be explained by beta 0 and beta 1. So in other words, well, it depends on where you are. If you have something X is, let's say this ratio is very, very, failure rate is very, very high when T is small. That means what? When X is small, when X is at the beginning, you have a very, very high odds ratio. That means you tend to fail at the beginning. That means what? Infancy fatality. But on the other hand, this ratio getting very, very big, not at the beginning, it's at the end of 90 years old, 80 years old. Oh, people tend to get COVID when X or T is large, equal to 80 or 90, but not at the very, very beginning. So this whole thing becomes odds ratio. If I take log can be explained by beta 0, beta 1. If I take the exponential on both sides, that means what? Your odds ratio could be big, could be small, depends on where you are. Your x is small or your x is big. The relationship, intercept and the slope, those parameters, you need to figure that out. So I'll give you one example. For example, if I have a beta 1, okay, is 2. So you're in a society, beta 1 equal to 2. I'm in a society, beta 1 equal to 20. That means that in your world, x equal to 2. I say x equal to 3. 3 times 2 is 6. Your odds ratio depends on exponential of 6. But in my world, sorry, I'm in a terrible world. My beta 1 is 20. X is equal to 3. 3 years old, 3 days old, I don't care. This thing becomes what? 3 times 20 is 60. So my odds ratio grow really, really bad. So some odds will transfer slow. Some odds will transfer very, very quick. So logistic regressions really is talking about how the odds, how my coins are more likely to have head or likely to have tail. My coins more likely to have survival or failure. Depends on an exponential of a regression. And that's the monkey games we're playing here. Okay? Exponential of these things. Here is your odds ratio. And your odds ratio really is t based on your mu location and a s or beta function. So people look at the function. First, generate t. Recover to your f inverse t by doing ft. 1 minus ft, you get st. St over ft. St over your ft, that's your odds ratio. And then you take your log of your odds ratio. Okay? And then when you plot your t against your log odds ratio, that should linearize it. Okay, I think I introduced something more than I explained last week. So I'll give you a few minutes to, not few minutes, few seconds, 60 seconds to raise your hand if you cannot visualize it. Everybody good? Young man, you have a problem? Or you're good?
So if you will go back to what you have to ask a question about the y-axis.
Okay, so the y-axis is the log odds ratio. I'm sorry. In this case, we're using the inverse of odds ratio. It's survival over the Which one you're talking about? You need to. Are you looking at?
Normal, log normal, but how do I go about the y-axis?
Oh, okay. And x-axis is log t, and y-axis is take the log of your log normal inverse. Here, first I'll let you look at your stuff, and then I'll go back to the cheat sheet, so you will see how that linearized work. Oh, I know. I have one here. Okay. Log t, no problem. Log normal inverse. Oh, I know. Remember, see if you agree with me. First, look here. This is originally we said that there's a t function. It's not normal, right? But if I take the log, it will be normal, right? And so that's exactly what I did. I have a variable t, and that t is not normal. But if I take the log, it will become normal. Got it? Okay. And you agree with me? We said here is a t. That invertible normal distribution, that is a t, right? But that t, technically speaking, is not normal. But if I take a log, it will become normal. So I take a log outside that inverse function. Agree? Okay. Yeah. So law logistics, and what we're doing is everything's the same except this time. So we have ft, st, st over ft, and then we take the log t, and finally we take the odds ratio log. Okay, so it become not odds ratio against not log odds ratio against t. It's log odds ratio against log t. So if you use this against log t, it will become a straight line. Okay? And what's the difference between the two? I already showed you here. Look, log logistics and log logistics. Logistic against log logistics. Y-axis exactly the same is the ST against FT. Okay? And what's the difference between the log logistic and log logistic is the T versus log T. Okay? And why you have another log? Because, well, it's log logistics. Okay? Okay, so your homework is really give me two things. Victoria, you want to take the notes for next Tuesday? Okay. First, repeat. I already have the file give you. Generate the plot. Linearize the following distribution: exponential, Pareto, Weibull, Gumbel, normal, or this 9 distribution. I want to see a line. And I want you to monkey around with the parameter, and you always get the line. You can tell we're doing this. For example, I changed the parameter to 1.5. Things change, but the line is always the line. So do something to make sure that the line always there. When you change the parameter, it doesn't change. So you have a set of template to play with. The other thing I would like you to do for every Excel, when you play with it, at the end, recover the T through F inverse T. Okay? And that's the big homework next Tuesday. Okay? Yes. Okay? Okay. So now, if we can generate a bunch of this mountain PDF, and then we can turn them into a CDF. of course, we need to figure out how to do that. That's the counting process to generate the distribution. And we'll cover that very soon. The thing is that why we need a distribution. We need a distribution to know how late is too late. Okay? I used to talk about when I was a kid, Chinese New Year, we'll have new clothes. But we also dress in the new clothes nicely. What we do, we play firecracker. And it's very dangerous things. And, we throw firecracker into other neighbors' septic tanks, stuff like that. And what will happen? All kinds of damage, right? And when you play, you basically say that I need to keep my clothes, my new clothes, in shape so you won't get into trouble when you get home. But from time to time, firecrackers are very dangerous, and you get burned, and your suit got, all kinds of troubles. So there is a point of no return. What does that mean? It means that once you play so badly, the damage is so hard to cover, you're going to get into corporal punishment when you get home at New Year time. So once you realize that things are so bad, what are you going to do? What do I care? Keep playing, and you become the roughest kids in the neighborhood because you're already in trouble. You might as well let other people in trouble. Okay? And so what I'm trying to say is, some things. Have you ever go out, play, your new bike or something new, and you did something, or skateboard. You try something really crazy, and you try to, survive. But there will be a point that you realize that, you damage something so bad, you basically say, what do I care? And once after that point, what will you do? You play totally in a different mode. So now I'm going to, yeah. Mm-hmm.
When I was like 4, I went to preschool,
Mm-hmm.
and they had bikes there, and I only knew the bikes with like the brake handlebars, not the pedal brakes.
Mm-hmm.
So I started going down this hill towards a fence, and then I didn't see any brakes on the handlebars. So then I was like, I'm brilliant.
Mm-hmm.
The wheel is turning. I can stop the wheel from turning. So instead of hitting the fence, I put my leg in the wheel, and then I guess I've never turned with the wheel after that. But I didn't hit the fence. So did you get my bullshit was
Oh, you guys know that guy is my son, right? Guess what I did to him? He was like 4. We went in Texas. There are, in the 90 Bush, they basically downsized a lot of Air Force base, and basically they want to downsize the Air Force. Cold War is over, and so we went to an abandoned Air Force base. I have faculty ID, so we went in. I have a big kite, okay? And then I put him on rollerblade, and I basically said that, let the kite, can pull you, see how far it can run. Guess what? How far he run? Off ground. Yeah. Well, okay. Try to share with you. Sometimes kids not that crazy, but the dad is is the one you have to worry. Yeah.
Let me ask you, what city that Air Force Base was in?
Lubbock, Texas. Yeah. Yeah. Not far away, there's another Air Force base. There are 2 Air Force bases. One is close to the New Mexico border, is Cannon Air Force Base, and the other one is Abilene. And they have B-1, B-2 bomber. That's totally different Air Force base. The one we went, there's nothing. Yeah, just flat, and yeah.
Because my mother's from Aberdeen and her father was
Really? Huh. Oh, I told you guys I worked for airlines before, right? The first things that really dazzled me was I was standing right beneath the nose gear of the 747. I look at this and I said, "Whoa, how can this sucker fly?" And this class, sooner or later, will cover a lot of, okay, can this thing still airworthy? Can this thing still, should we change our behavior since this thing is not survivable, or the chance of surviving is getting less and less, okay? And this is something I would like to cover, and all three story, okay? Your bicycle story, my rollerblade story, they all relate to this. People look at the blue region of a distribution. If this is a bell shape, that's my alpha, right? And usually alpha equal to 0.01 or 0.05. And why we set the alpha as that level, we basically said that if, okay, the p-value is less than 0.05, means that whatever you observe, the region is less than blue, I consider, I don't believe you anymore. I reject the non-hypothesis. So the non-hypothesis is that it's not survivable anymore. So if I have a blue region, okay, that blue region is defined by a VAR value. VAR, put it down, is value at risk. If my value at risk, and sometimes the notation depends on, people writing VAR, they write the epsilon sign, V epsilon R. But no matter what, is your value at risk at this level. Okay, and usually what that is the point of no return. And people actually even, they call it expected shortfall in stock market. Now sometimes if the price dropped to say $100 per whatever, the stock dropped to this level, stop buying. Or when these things reach certain height, stop selling. And so VAR, later on I'll explain, a lot of times it's psychology. You decide when you want to do something. But would you agree with me? If I have a mountain and then I make a cut called VAR, then it will generate a blue region. That blue region is my tail value, or we call it beta value. And beta value equal to what? From VAR integrate to infinity of my PDF. Agree? Okay? So now if I have a beta value, okay, I can translate this into my CDF. So from here to the ceiling is 0 to 1. And if from here to here is 1 minus beta, where is beta? It's from here to here, right? This high is called beta. Would you agree with me? Here, the whole thing is 0 to 1. If I said that, okay, I would like to set up a ceiling clearance called beta, tolerance called beta. So from ceiling to this dashed line, horizontal line is beta. Then from 0 to this horizontal line is 1 minus beta. Agree? Because beta and 1 minus beta is total. So now we transfer our game from beta in the CDF, in the PDF to the CDF world. In the CDF world, we will have three regions. The first region is from ceiling to here. This is what we call I3 region. This is the most important region I'll explain in a second. And then the second region is from beta. I'm sorry, from the expected value. Whatever the expected value to the the red VAR region. This is called I2 value. And the third value is from 0 to the expected value. This is called the I1 value. Okay? Let me focus on I3 value. I3 value is what we call CVAR, conditional value at risk. The whole semester from now on, you're going to hear me, nagging about CVAR all the time, because it's about survival. It's decision for survival is decision for reliability. CVAR equal to VAR and beyond. What's beyond is the I3 value divided by beta. So people look at this, think with me together. First, is VAR getting bigger and bigger? CVAR is always bigger than VAR or less than VAR. What CVAR and VAR, which one is big? CVAR equal to VAR plus I3 minus beta divided by beta. Which one is always big? VAR big or CVAR big? CVAR big. Because why? Beta, remember, is a percentage, 0.01, 0.05, point something. So beta is a positive value, agree? And then what is the I3 value? I3 value is beyond, is that red region. I3 region is from VAR to infinity. How much 1 minus FT is really your ST? That means that, I decide, I'm going to change my oil or whatever I will do. Here's my decision line. At my decision line, how much survivability, how much I3 left? Okay? And usually what we're really trying to play is try to figure out this. Okay? When VAR increase, people, next question. When VAR increase, beta increase or decrease? When VAR getting bigger and bigger, I'm going to say way, ho. VAR increase, beta will decrease. Agree? I3 will increase or decrease? Also decrease, right? Because this line is moving to the right, it's getting smaller and smaller. So in other words, is that when you say that, hey, I'm going to wait, VAR increase, both I3 and beta getting smaller and smaller. See, in other words, the residual value is getting smaller and smaller if you keep waiting. So in other words, now back to my firecracker for New Year's close. If you wait, you realize is what? Man, there's not much left. If there's not much left, what do I care? But on the other hand, okay, would you change oil every day for your car? That means if you put your VAR very, very early, even before your expected failure time, that means what? If your VAR extremely small, your beta will be big, your I3 will be big, but that is what? You basically said that, man, my car's still good, but I just want to waste money, start changing oil, start doing a lot of stuff. Then your I3 will be big, your beta will be big, but it's a lot of waste. So sooner or later, you basically need to decide what? The VAR should be wait, how long I have to wait, is reasonable wait. What is reasonable? Means the investment of your money and time, you're going to get the residual back. And there will be a point, basically said that I'm not going to do anything about it. Okay? Before I let you go, I'll ask you this. If you're the teacher, okay, and you have A student, B student, C student, D student, F student, okay, and now you said that I'm going to devote 2 more hours to teach the students so they can do better in reliability and survival analysis, would you spend your time on the A+ student? They'll be fine with or without you. Would you spend time on the F student or D student? You still feel like, man, they don't care. Whatever you do, nothing gonna happen. So you need to make that line. Basically says that, okay, I invest, and then I can recover some I3 and beta if I set up the threshold right. So maybe at a C level, maybe at a B level. So the money I put in, I can move a bunch of people from not surviving to surviving. I can maintain a lot of wind turbine, a lot of airplane, from not airworthy to airworthy. And that's the reason why we need to figure out how to model the distribution, figure out based on the data, what is that distribution, and then use that distribution to decide where to make the VAR cut. And what is the performance of the VAR, and that distribution will be CVAR equal to VAR plus I3 divided by beta. Okay, sayonara. See you Thursday.